So I thought in this somewhat short talk, I give an overview of quantum computing and also the applications that we're thinking about at Zapata. Hopefully this is useful to you. So I want to start with making the point that how computing as a human activity has evolved over the period of history as our understanding of physics improves. So we went from initially the purely mechanical device, which is an abacus, and then with thermodynamics understanding, we learn how to build steam engines. And then this is the first conception of a computer, which is powered by steam engine. It never actually came to fruition, but it's worth noting that as early as 19th century, people are thinking about that already. And then there are special purpose computers that are purely mechanical, that are intended for computing specific quantities like areas and volumes. And then electromagnetism developed in physics, and then that boosted computing to the next increment where you can actually do some very sophisticated tabulation. And I think in the 1890 US Census was the first instance where a computer actually outperformed the human. So this is the first instance where you have to use computer to process that much data instead of using human intervention. And then I think the mathematicians and scientists thought a bit deeper about what it means to compute in the first place. For example, Alan Turing and John von Neumann thought deep about the models of computation, and that underlines very much the architecture of the modern computer. So, but at that time, the electronic computers are still based on vacuum tube. And then quantum physics developed in the early 20th century, and with that insights that led into material science, then developed the transistors. As a result, the computing devices become more and more efficient. And then we kicked off this decades of industry trend called Moore's Law. This is the empirical growth of how traditional computers are developing. And then it was, I think, in 70s and 80s where there's new notion of quantum computing and quantum information, which is to ask how we can use quantum physics for the purpose of information processing. And this is a fundamentally new viewpoint, which became the intellectual foundation that later on gave rise to the breakthroughs in quantum computing, and also the field that we know today as quantum computing. So the point here is that you can see how computing machines grow incrementally as how our understanding of physics improves. And also the fact that quantum computing, the quantum physics is not the news here. The real news is how can we use quantum physics in a unique way to process information. Just a very high level description about quantum computer. So you have a collection of basic units called qubits. And then in this example, there are 3 qubits, which can exhibit one of the 8 states. And then you start with some initial state of the qubit, usually all 0. And then you go through some coherent manipulation of the state of the qubits. And then you obtain a measurement result. And this represents a fundamentally different way from the classical way of solving a problem. So if you think about solving a problem as finding a needle in a haystack, classical computers sort of has this deterministic path in a haystack. But on the other hand, quantum computing, because of the unique advantages or unique properties of quantum mechanics, allows you to search in the search space in a fundamentally different way than classical computers. So if you observe that as the number of qubits grow, the number of states that the qubits can be in grow exponentially, and it doesn't take until a moderate number of qubits that you have the number of states that parallel some of the astronomical numbers, like the number of hydrogen atoms in the universe. So this is really a staggeringly large state space that the state of these qubits live in. And then some of the early insights about what you can do with a fault-tolerant quantum computer include integer factorization, unstructured search. So this is Grover's algorithm, and also quantum simulation. So these are some of the early insights that propelled the field, and some of the early excitements. And then there's also a sort of diverse range of physical mechanisms that has been proposed for realizing the quantum computing scheme. So the scheme that I presented a couple of slides ago, it's an abstraction, and under the hood, there are multiple physical mechanisms that supports the notion of a qubit that can be coherently manipulated as a quantum algorithm. And then we have also seen some of the commercial players like IBM and D-Wave proposing varieties of models of quantum computing. So if we look at this history of computing, if we zoom in to the 20th century, to the recent modern computing, and look at how sort of computer science as a discipline unfolded as the decades passed. So we start with the mathematical aspect, the formal models of computation. So these are purely abstract concepts. And then as computers became more mature with fields such as programming languages, and then we want to think more formally about these computation, which gave rise to computational complexity, algorithm data structure. And then more recently, we have networking, parallel computing, and of course, machine learning. So all of this also underwent this process where initially the primitive computers can solve some very small toy problems, and in order to make full use of these early computers, one needs to be very economical. One needs to be very conscientious about the memory and about the details of the computational hardware in order to make full use of the computing device. So this is a concept that is not very, this is a concept that's a bit foreign today, because we have our computing device today are largely abstracted away from the user, who is largely agnostic to what happens in the hardware. But it's good to keep in mind that in the early days, there used to be this design pattern where the program needs to be very conscientious about the computational resource. And then decades after some of the first systems, we have fault-tolerant computer systems, which are systems that don't really that can stay online for a very long time without computational error. And then the progress that's happening in quantum computing is essentially to take this decades of computer science and compressing it into just a matter of a few a small number of years, where in accordance with computational complexity, we have quantum computational complexity, and basically for each and every area of computer science, there has been studies about how quantum mechanics could impact each and every one of them, and all of that is happening at a very compressed and accelerated time frame. So if we zoom further into the recent 20 years, and we can see this explosion at even closer, at a closer distance. So D-Wave has been advocating their quantum annealing approach for building quantum computation. And then there are also many companies promoting gate model quantum computers, starting from IBM's Quantum Experience, which is a quantum processor that is accessible publicly, that can execute quantum experiments. And then there are multiple other companies that have promoted, that have announced devices of varying numbers of qubits. And then IBM announced, for example, the 20 qubit device that can be accessed through the cloud. And then some of you must have learned in late 2019, Google announced the quantum supremacy experiment, which is an experiment done on 53 qubits Sycamore device. And then we have seen a couple more announcements recently about more startups and corporations jumping into the quantum computing field. And then there's also a lot more that are not covered here, but this is just to show you the pace of the pace of the field, how the pace has been picking up. So returning to this abstraction of quantum computing, where we basically carry a set of qubits through a coherent quantum evolution to land at a particular measurement outcome. In reality, there's a bit more subtlety, where the environment interferes with the quantum computing process, and this is the devil that we want to fight against, because of decoherence, because of the disturbance from environment. the qubits may lose their quantum properties, and the physics becomes classical, which means we're no longer able to tap into the power of quantum mechanics. And thankfully, there's an elegant set of research in the past decades developing error correcting schemes that protects the noisy physical qubits from error. But the state-of-the-art error correcting techniques require each physical qubit require thousands or tens of thousands of physical qubits to represent one perfect qubit. So there's a very large overhead. And a couple of years ago, there's a resource estimate that that is intended to calculate how much quantum resources is needed for calculating, let's say, quantum chemistry problems. And it seems that one needs millions of physical qubits and hours of quantum computing. And that is in stark contrast with the state of the hardware today, which has less than 100 qubits, and the quantum computing computation lasts for less than 1 millisecond. So then the question is, what useful applications can be found before we get to fault tolerance, before scalable fault tolerant quantum computers are built? And this is getting to the point about noisy intermediate scale quantum devices. So this is the era that we're in right now, the era of NISQ devices, and where quantum hardware providers are constantly improving the amount of computational resources that they can offer on their hardware platform, including how well they can control their qubits, how well they can execute elementary operations on the qubits, how are the qubits wired together, basically which qubits can talk to which qubits, and then this is the state preparation and measurement error. So all of this builds on decades of quantum system and electrical engineering efforts. And then at the same time, on top of the hardware, there are also different layers of quantum software, and we need to optimize all layers of abstraction, basically to drive towards useful near-term quantum applications. So this is getting back to the first point about in the early days why the computer scientists will need to be very conscientious about the amount of computational resources that are on the quantum device, that are on the classical device. And we're in a similar era where in order to make full use of noisy quantum device, the programmer needs to be very mindful of the specific computation, the specific details of the hardware in order to extract the most out of a given quantum computer for near-term applications. So this gets to the core mission of Zapata. So just very quickly go through the summary of what we do. So one is our mission is to be able to deliver a quantum advantage to enterprise customers, and our founding team has some of the leading experts on quantum information science, and then we've raised some funding, and we have customers in these industry verticals. So I was just talking with Catherine that before the talk that it has been an eye-opening experience trying to apply the concepts in quantum computing into these domain verticals. So I'll talk a little bit about our product. And also I'll show a few examples of what concretely one can use quantum computers for. What are the customer use cases for near-term quantum devices in these specific application areas. So for NISQ devices, which has a small number of qubits, the overall strategy is what we call classically divide and quantumly conquer, because because quantum computers are essentially very special purpose devices, and there are tasks there are many tasks that can already be carried out very well on a classical device, and quantum computing in this sense is essentially a processor that 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 the classical computer offloads specific subroutine of a workflow onto. So here, typically a problem is partitioned into a particular form that is compatible with quantum algorithms, and then there's some pre-processing that happens on the classical computer, and then that essentially exposes the core part of the problem that you can solve on a given quantum device, and then this is offloaded to the quantum computing workflow, and then when we get the results from the quantum computer, those are integrated back into the existing solution on the classical device. So in order to make this happen, there are clear architectural challenges. The first is framework compatibility. So some of you who have experience with some of the quantum computing programming paradigms probably have worked with Qiskit, or Google has Cirq, or Rigetti has Quill, or probably some other quantum computing programming paradigms. And each programming paradigms have their own strengths and limitations. So how do we make the most out of these frameworks? So this is a problem that's one architectural challenge that's present in quantum computing. And another one is to deploy on computing resources. So this is because we need HPC resources for carrying out the pre-processing and post-processing, and also quantum computers today. Many of the hardware providers also provide their devices through the cloud. So there are deployment issues that prevents this pipeline from being implemented very smoothly. And then also there's a matter of data management. So how can we, especially for machine learning applications, how can we efficiently wire the data from the quantum computers and integrate it into the classical workflow? And another part is about reproducibility, because those solutions are highly complex and largely involves more than one person. And so how do we make sure that the code that one person writes is reproducible by another member of the team, and also the code written by oneself in the past is reproducible today. So these are architectural challenges that are certainly not unique to quantum computing, but they all exist in terms of practical applications of these quantum devices. So to overcome these challenges, we need a modular, extensible, and reproducible infrastructure. And this is just to add more color to the statement about the architectural challenges. So this is one particular example of a quantum solution. So a computational solution involving a quantum computer for solving a quantum chemistry problem. And you can see there are a few dozens steps. And then there is only this one step that is executing instructions on an actual quantum computer. And then all of this is in classical pre-processing and post-processing. And so these are built specific for the purpose of quantum computing. And so it's by no means plug and play. And probably most of the quantum solution is in fact, at least as far as the number of steps are concerned, most of the steps are actually in the classical domain and for classical pre and post processing. So this motivates us to build an environment that facilitates this type of applications, where we start from the library level, where we have Python scripts and Jupyter notebooks, the kind of programming environment that researchers are very familiar with. And those libraries can be executed in the container environment, and the containers produces artifacts as data that can be passed between different containers. And then the whole orchestration of how the containers and artifacts form a network is the overall workflow of the quantum solution. So we have, for example, built for multiple libraries and multiple kinds of quantum hardware, and also for a database backend. But the highlight is that we need a containerized environment to be able to handle the sort of different kinds of frameworks and different environments. And also we need a workflow system to make sure that the workflow is reproducible. And the goal is to make the implementation scalable so that we can build these immensely complex quantum solutions without losing sight of for example, different environments and different frameworks and these details. So it essentially unifies the different layers of abstraction that we talked about. So at the most fundamental layer, there's the NISQ hardware, and then on top of that, you have the compilation and the quantum application, and then the workflow execution. So this is essentially what we want to drive towards is something that is agnostic across the stack. So it's not only agnostic to the quantum hardware backend, but also that you can also swap in and out the library functions and also the database endpoints, and basically each component of the software workflow. And the result is to de-risk quantum capability building and avoid vendor lock-in. So some of the organizations that we talk to, they want to get into quantum computing, but immediately they face the choice of, okay, should we go with IBM? Should we go with Google? Should we go with Rigetti? What kind of software tool should we use? And how do we pick the right solution or the right framework to start building or to start looking into quantum computing? And we want to be able to create this environment where one can essentially de-risk the vendor lock-in. So just to show concretely what this looks like, basically, we want to be able to build things to a place where by changing a simple label, by switching a simple entry in the workflow file, you can switch between different quantum hardware. You can switch. So in this case, I think you can switch between IBM Qiskit and Rigetti by minor change to the workflow description. And also the artifacts coming from the container allows for managing the data. So in this case, it's a data coming from training a quantum circuit for capturing a probability distribution. So this is a very common task in machine learning, where you're training a machine learning model to learn the probability distribution of training data. So I want to show some representative quantum use cases. So we have looked into several areas such as chemistry, optimization, machine learning, and stochastic simulations. So chemistry is something that we started from even before Zapata. I think 5 of the 6 co-founders are coming from the laboratory at Harvard, and a main focus back then for us was to look at chemistry applications, and then we expanded into these other areas. So this is a customer collaboration where we looked at, and this is published material, so for details you can look at this paper in the archive. So what we did was that we looked at different. So the customer is an oil and gas company, and the primary interest is to compute the chemical properties of these organic molecules, and so what we did is we benchmarked the cost of computing the properties of these organic molecules the so-called variational quantum eigensolver. So this is a very well-known method for quantum chemistry calculation on near-term quantum computers. And what we did was that we performed extensive benchmarking, and we found that the measurement cost, so the number of times one needs to call the quantum module for even a basic step of this chemical calculation, requires an impractical amount of resource. So this was something that was not apparent to us, at least before the project. And then it is in the process of actually applying this technique, which we knew very well coming from academia. It is in the process of applying this to the actual problem instances that really revealed this bottleneck that was apparently making, for example, a single energy evaluation taking, in this case, 18 days or even longer. So it's clear that new ideas are needed. So what we proposed, what we used as an improvement was that we have this foundational method for extrapolating, or for interpolating between two extremes of quantum algorithms. So the basic thinking is that this variational quantum eigensolver was one particular variant of quantum algorithms that takes into account the limitation of near-term quantum devices. And then there's in the textbook, there's the more there's another type of quantum algorithm that has a different trade-off than VQE. And in the case of VQE, it requires a small number of operations to be performed on a quantum computer, but it requires a large number of measurements. But on the other hand, for the phase estimation, this requires a very small number of measurements, but it requires many operations to be able to be performed on the quantum computer. And we realized that this is in some way a false dichotomy, and we introduced this technique, which Bayesian technique, which we call engineer likelihood function, that smoothly interpolates between these two regimes. And I won't be able to go into the details, but at a high level, you can see the overall setting is we run a specific circuit on a quantum computer, and then the quantum computer enables us to implement essentially a specific kind of likelihood function. So if you know about Bayesian inference, you probably know that the likelihood function is what updates the prior and create the posterior. So it's a crucial piece that allows us to extract information, and this is essentially what we take advantage of. The quantum computers are able to implement likelihood functions that are otherwise not likely to be implementable on a classical device. So we take advantage of that, and we're able to perform Bayesian inference, and this scheme essentially interpolates between these two extremes, and then this is what allows us to get as much speed up in amplitude estimation as possible on a noisy quantum computer. So this is sort of our response to the roadblock. So another example I want to show in optimization, and this is in collaboration with IBM, and this is also published on the archive, so we can read about more details. So here we're doing a case study where we're trying to use near-term quantum devices for factoring. So you probably heard about quantum computer being able to factor large numbers and therefore break some of the well-known encryption schemes like RSA. This is different. So this is different from Shor's algorithm. This is a different approach to optimization, where we think of optimization as essentially multiplication backwards. And we want to optimize the assignment to these variables such that this multiplication table is satisfied. So it's a fundamentally different approach to Shor's algorithm. And we're sort of using the factoring as a case study, and we want to see how it plays out on a real IBM device. So previously in the slide, I mentioned this framework of classical pre-processing and quantum computation, and then you have the post-processing. So this is one embodiment of that architecture, where you have the pre-processing that takes a number that needs to be factored, say 143, and then it does the pre-processing that, for example, infers as many variables as it classically can, and then take the remainder of the problem and transform it into an optimization problem, and then pass it to the quantum processor, and then the quantum processor will aim at finding the remaining the value of the remaining variables, and then integrate it back into the solution that came from pre-processing. So that gives you the factors that multiplies to the initial number provided. So we did some very careful observation. We did some very careful experiments on the IBM backend, and then we have some bonus discovery. So we found that there's some coherent noise on the IBM device that was not captured even by the noise model in Qiskit. So we had some interesting experiments that eventually allowed us to explain what accounts for the discrepancy between the ideal case and the experiment case. But this is more of a sort of bonus discovery that is quite interesting. That form quite an interesting part of our journey, and this is basically what it looks like running an experiment on a quantum computer today. Is that you may find new things that could very well be unaccounted for even by the hardware providers themselves. So I want to show some cool experiments that we did with machine learning. So and this is one example that I think is very worth talking about, where we used 8 qubits coming from ion Q. So this trapped ion. So it's a different physical system from IBM, which is based on superconducting qubits. So we take we ran circuits on the 8 qubits trapped ion device, and we take the measurement outcome and use it as a latent space sample for generating handwritten digits images. So this architecture is a generative adversarial network, and the goal is to generate these handwritten digits given the training data of many handwritten digits. So if you know about deep fake, this is basically sort of deep faking handwritten digits. And with the same technique, you can very well do deep fake for human faces or for other high dimensional data. And then, so what we did is we have this architecture for generative adversarial network, part of which is hooked into an 8 qubit quantum device. And then as we train this quantum classical hybrid neural network, we monitor the inception score, which describes the quality of the output digit. So as you can see, all of these are handwritten digits generated directly based on data coming from the quantum computer. So they don't exist in the training data set, but these are completely generated by computers, and they certainly look quite realistic. And if you really compute the inception score and compare it with a classical benchmark, and in this case we use the direct convolutional GAN, and you can see that there's this difference where the output from the quantum model is slightly above the output coming from the DC GAN. So the squares are the classical benchmark, and then the circles, the orange circles, are the output from quantum device. So this is only on 8 qubits, and this is what we did last year. And we were very encouraged by the results, because in principle, you can simulate 8 qubits on a classical computer. It's not hard, but if you really set the rules of comparison properly between the machine learning models, you could actually see the difference in terms of capturing the correlation in the training data. So just to animate this process. So we start out with digits that are fairly blurred, and as the training progresses, the data become progressively more realistic, as they usually do when you train a generative adversarial network or any other generative work. And this was done with Orquestra, so the workflow management system that I mentioned before, in conjunction with IonQ hardware. So yeah, so we noticed that there was another laboratory in China that was trying to do the same thing, but we were able to get much better solution. So what can we do with these generative models beyond the sort of deep fake flavored machine learning application? And this is another one I think is quite interesting, where we use the capability of a near-term quantum device for generating new data points, and we tap into that capability for enhancing optimization, combinatorial optimization. So probably a lot of you in your own research or work have to solve optimization problems where you have a list of candidates, and then each candidate has a particular fitness value or particular cost, and you're trying to optimize the cost for a given candidate. And you start with this list of evaluated candidates as a training set. And then what we do here is that after some simple filtering where you pick out where you favor the more where you favor the better candidates, and then you form the training set. So what we do here is that we use a quantum enhanced generative model to learn the distribution of this training set. And then once trained, this model can spit out new candidates. And these new candidates are grouped into the pool of evaluated candidates. So we tried this we tried this scheme for portfolio optimization methods, portfolio optimization applications for S&P 500, and it seems that for a classical algorithm, the quantum generative model, or the generative model here, was able to propose solutions that are otherwise that are otherwise not discovered by the algorithm. So this is essentially, you can think of this as a boosting engine to an existing optimization pipeline, where you can have your existing optimization algorithm running business as usual, but you have this machine learning, hybrid quantum classical machine learning, that are watching and observing closely the trace of candidates that are being attempted, as well as their objective function values. And then the generative model learns this distribution and was able to propose new candidates that are previously not covered, likely not covered by the classical candidates. So it broadens the search space in an intelligent way, and that is sort of one example application that we have already fleshed out based on this quantum generative model that I presented before. So that's sort of hopefully gives you a flavor of the kind of things that that are possible with quantum computers today. And so I just want to wrap up very quickly, and then people can ask questions. So obviously, quantum computing is an emerging field with a lot of things going on in both hardware and software side. But the near-term focus is to see, what are the truly impactful use cases, and by impactful, I don't mean just from a computational standpoint, but really impactful from a business standpoint. And then associated with that is, how do we build software tools so that we can overcome some of the architectural issues that I mentioned before. And then this is a point specifically true for us as Zapata, where we want to look towards building production systems that are actually deployed, instead of only staying in the R&D prototyping phase. And yeah, so Zapata is very excited about basically how to push these technology into real industry use cases.